Launching a rocket is dramatic. Flying past the moon is historic. But the most dangerous part of the Artemis II mission isn't either of those. It's coming home. When the Orion capsule hits Earth's atmosphere, it will be traveling at roughly 25,000 miles per hour. That's Mach 32. The air in front of it will compress so violently that it turns into plasma, heating the spacecraft's exterior to over 5,000 degrees Fahrenheit. For several minutes, nobody on the ground will be able to talk to the crew. And the only thing standing between 4 astronauts and that inferno is a heat shield that everyone already knows has a problem. This is the engineering story of how you bring humans back from the moon, and why this particular re-entry matters more than any since Apollo. To understand why this is so hard, you need to understand how different a lunar return is from what we normally do in space. The International Space Station orbits about 250 miles above Earth. Spacecraft coming back from the ISS re-enter the atmosphere at around 17,500 miles per hour. That's already incredibly fast, but it's a known quantity. We've been doing it routinely for decades. Coming back from the moon is a fundamentally different problem. The Orion capsule will be traveling at about 25,000 miles per hour, roughly 40% faster than spacecraft returning from the ISS. So that means about twice the energy the spacecraft has to dissipate. All of that extra energy becomes heat, and it hits fast. Within minutes of touching the upper atmosphere, temperatures on the heat shield surface will exceed 5,000 degrees Fahrenheit, nearly half as hot as the surface of the sun. At those temperatures, the air itself ionizes into plasma, forming a superheated sheath around the capsule that blocks all radio signals. Mission control goes silent. The crew goes silent. For several minutes, nobody knows what's happening inside. This is why no spacecraft designed for low Earth orbit can simply be sent to the moon and back. The thermal environment is in a completely different category, and it's why the Orion heat shield is the largest ablative shield ever built for a crewed spacecraft. 16.5 feet in diameter, designed specifically for this problem. Orion's heat shield is covered in a material called AVCOAT. It's an ablative material, meaning it's designed to char and erode away in a controlled fashion, carrying heat away from the spacecraft instead of letting it reach the crew cabin. It's the same type of material used on the Apollo capsules, though the manufacturing process changed significantly. During Apollo, technicians filled over 300,000 individual honeycomb cells by hand with AVCOAT, a process that took months. For Artemis, Lockheed Martin switched to 186 pre-machined blocks bonded onto the capsule's titanium skeleton. Faster, more efficient, and it was supposed to work the same way. It didn't. When Orion returned from the uncrewed Artemis I mission in 2022, inspections revealed damage at over 100 locations. Instead of eroding smoothly, the AVCOAT had cracked and large chunks had broken off, a process called spallation. The cause, after 2 years of investigation and over 120 individual tests, the AVCOAT blocks weren't porous enough. During re-entry, gases formed inside the material but couldn't escape. Pressure built up beneath the surface until pieces just popped off. The boundaries between the blocks correlated with the worst damage. Now here's the critical part. By the time engineers understood the root cause, the Artemis II capsule was already built. The heat shield was already attached. Replacing it would have meant years of additional delay. NASA had 2 choices: wait and rebuild, or fly with the existing shield and change the mission to reduce the risk. They chose to fly, but they changed how Orion comes home. During Artemis I, Orion used something called a skip re-entry. The capsule dipped into the upper atmosphere, used aerodynamic lift to bounce back up briefly, then plunged back in for final descent. It's an elegant technique, first used by a Soviet probe in 1969, that extends the range the capsule can fly to reach a precise landing spot. But it's exactly what caused the heat shield problem. During the skip phase, when the capsule briefly left the atmosphere, the heating rate dropped. That sounds good, but it actually let thermal energy accumulate inside the AVCOAT without forming enough char to vent the gases. Pressure built up. Chunks broke off. For Artemis II, NASA replaced the full skip with what's called a lofted entry, a much shorter, gentler version that avoids the prolonged cooling phase that caused the gas buildup on Artemis I. This decision came with real trade-offs. The skip reentry gave mission planners more flexibility in choosing where Orion splashes down. Without it, the landing zone is more constrained. They have less range to work with. It also narrowed the available launch windows by about 50%, which is one of the reasons getting Artemis II off the ground was so difficult. But the steeper profile keeps the heating pattern in a regime where engineers have much higher confidence the AVCOAT will behave predictably. NASA conducted over 100 additional tests at facilities across the country. This is the first time this specific profile will be flown at lunar return speeds with humans aboard. Reentry is the real test. Let's walk through exactly what happens during reentry, because it's a remarkable sequence of engineering. It starts hours before Orion touches the atmosphere. The crew performs final trajectory correction burns using onboard thrusters, tiny adjustments to make sure the capsule hits the atmosphere at exactly the right angle. Too shallow and it skips off into space. Too steep and the deceleration forces could be dangerous. At about 400,000 feet above Earth, the European service module separates. It's done its job: propulsion, power, life support for the journey. And it can't survive re-entry. It burns up. From this point on, the crew is in the capsule alone. Then the heat shield takes over. As Orion plunges deeper, the air compresses and heats. The AVCOAT begins to char and ablate, burning away by design, carrying thermal energy with it instead of conducting it into the cabin. During Artemis I, even with the unexpected damage, cabin temperatures stayed in the mid-70s Fahrenheit. The system works. The question is how cleanly the material behaves under this new, steeper profile. At peak heating, the plasma sheath forms around the capsule. Radio signals can't penetrate ionized gas. Communications black out completely, both for the crew and for mission control. Everyone waits. During the steepest part of re-entry, the crew will experience up to 3.9 Gs, nearly 4 times their own body weight pressing them into their seats. As the capsule descends and slows, the plasma dissipates and communications return. But Orion is still traveling at roughly 325 miles per hour. Far too fast to land safely. This is where the parachute system takes over. At about 25,000 feet, the forward bay cover jettisons. 3 small parachutes pull it clear of the capsule. Then 2 drogue parachutes deploy, each about 23 feet in diameter. Their job is to stabilize the capsule and slow it to around 100 miles per hour. Next, 3 pilot parachutes pop out, and each one extracts a massive main parachute. These are enormous, 116 feet in diameter, 310 pounds each, made of a Kevlar and nylon hybrid. Together, the 3 mains slow the capsule from 100 miles per hour down to about 17 miles per hour. The entire parachute sequence, from forward bay cover to full main deployment, takes roughly 10 minutes. 11 parachutes in total. The system is designed to land safely, even if one main parachute fails entirely. Splashdown is targeted for the Pacific Ocean off San Diego. Navy divers from the USS John P. Murtha will be waiting. As Artemis II flight director Jeff Radigan put it, it's 13 minutes of things that have to go right. Here's what most coverage won't tell you. What happens to the heat shield after splashdown matters almost as much as the splashdown itself. After the crew is extracted, the Orion capsule will be recovered by the Navy and shipped back to Kennedy Space Center. Engineers will remove the heat shield and inspect every inch of it, mapping every crack, every char pattern, every area where material was lost. They'll compare it against their models and against the Artemis I damage. If the steeper entry profile worked as predicted, minimal spallation, controlled ablation, it validates NASA's approach and clears the path forward for Artemis III, which already has a redesigned, more permeable version of AVCOAT in production. The program stays on track. If the heat shield shows unexpected damage again, even if the crew is safe, it raises serious questions. Not just about the material, but about whether the models are trustworthy. The crew can come home safely, and the heat shield can still tell a troubling story. That delayed verdict is what makes this reentry unique. It's not just the end of a mission, it's the beginning of an answer that the entire Artemis program has been waiting 3 years for. Getting to the moon is the headline. Getting home is the engineering. When Orion hits the atmosphere, a 16-foot disk of ablative material and 11 parachutes will be the only things standing between 4 people and the Pacific Ocean. If everything works the way it's supposed to, most people will barely notice. That's the mark of good engineering, when the hardest part looks easy. But now you'll know exactly what it took.